Good morning.
Good morning, Professor.
Okay, so last class we ended at Euclidean algorithm and also doing the Euclidean algorithm backward or doing it recursively to find the linear combination of the two integers that equals to their GCD. Right, so this is the example I left you last class. So I hope you practice this question on your own. So first we want to find the GCD by Euclidean algorithm. So we know we will start with the larger number, right? So that would be 252. And we will see how many times does 198 go into it, and it will go into it once with a remainder of 54. And then we shift the 198 up and 54 up. And now we will see how many times does 54 go into 198. It will go into it 3 times with a remainder 36. In 36, again, if we shift it up, we will check how many times that 36 go into 54, and it will go into it once with a remainder 18. And then we shift it again. 18 will go into 36 twice with the remainder 0. And once we hit 0, we know the GCD will be the line above. Right, it will be the line above 0. So we know this GCD will equal to 18. Any questions here on how we get the GCD using the Euclidean algorithm? Are we all okay with it? Okay. Now to find the linear combination, we will do this process backward. Right, so start from the line we find the GCD. But since we want to write the linear combination in terms of the GCD, which equals 18. So we will start from the 18 and we want to write 18 as linear combination with the other integer. So for 18, we will have 54, and then we want to minus 36 times 1 to the other side. And then this, since we want to put it into linear combination form, we will have 54 times 1. And then instead of subtract 36 times 1, we will plus 36 times negative 1, by putting negative in the parentheses. Now we have a linear combination of 54 and 36. But we want to have linear combination of 198 and 252. So we will move a step up. Right? So starting from the line you find the GCD, you put it into linear combination, and then you will keep substituting by the previous line. and you will always substitute the remainder. That's how you know which number to substitute. So here we want to substitute 36. So for this 36, you want to write it as the linear combination. So you have 198 times 1 plus 54, and then you put the negative inside the parentheses. Right, just like how we did before we did linear combination. Now we will substitute those to 36. So you will get 54 times 1 plus, now we substitute that to 36, and then we times -1. And since we messed up the linear combination form, then we need to rewrite it. So we still can everyone hear me? And can everyone see the screen? Okay, sorry because I just got disconnected. Okay. So if you look at here, right, we want to rewrite it. So so we have it in the linear combination form. So here we see the 54 and 54. So we want to combine the 54. So we have 54 times 1. And also we need to distribute the -1. So we have -3 times -1, that will give you +3. Cross the 1 outside, that will give you 54 times 4. And plus 198 times 1 times -1, so that will give you -1. So if you're following the step in of my order here, it will always be you combine the number outside the parentheses. And then when you combine the lighter, you always change the number in the parentheses. Now you just put the GCD 18 into the linear combination of another two numbers, 54 and 198. But this is still not the number, the pair of number you are looking for, right? Since you are not all the way to the top yet. So you will move one step up, and the next number you will substitute 54, and 54 is here. So you will write 54 as a linear combination of 252 and 198. Again, you put the negative in the parentheses. Now copy down the rest. And again, you want to put into linear combination form again. So you have 198. Then when you distribute the 4, you have -4 plus the -1 outside. So you have 198 times -5 plus 252. You have 1 times 4. So you have 252 times 4. So now you have a linear combination of 198 and 254, or 252 equals to their GCD 18. So if you look at it, here is your T, and here's your S. Any questions here? Okay, I see people asking, you are thinking both 54 and 36 can be substituted. Okay, well, to do this process backward, whenever you do substitution, we will do one at a time. And I see people asking, why don't we do that from 18? We did it from 18. We always start with the line we find GCD, right there into linear combination. And then we will substitute one at a time. And I see people say substitute twice doesn't work. What do you mean by substitute twice? Well, every time when you substitute, you will eliminate a number, right? You will change your the pair of linear combination. So when you have 18, when you rewrite 18, right, from the GCD, you have linear combination of 54 and 36. Now, after you substitute the 36, then 36 is gone. Then after simplifying it, you will have linear combination of 54 and 198. So you should only substitute the number one at a time. And how do you know which number to substitute? Always look for the remainder. Start from the line, you find the GCD, and then you always go one step up, and then you will keep going up until you reach the first equation. So here, if you substitute 36 and 54 at the same time, then when you simplify it, your equation, right? So for when you substitute the 54, you will have 54 in terms of 52 and 198. Then you don't have 54 anymore. But when you substitute the 36, you will have the term 198 and 54. Then you will still have the term 54, which you already substitute. Then when you simplify it here, you will get 3 terms instead of 2 terms. So that's why you should always substitute one at a time. But every time when you substitute, one of the term will be gone since it's being substituted. Does that make sense? So you will always substitute one number at a time. Now you might see some scenario where maybe one of the term where the divisor and the quotient is the same. Even in that case, you only substitute one number. You don't substitute both. Okay, then let's move on. And we will come back to current algorithm and doing it backward to find the linear combination later. Okay, so next, if we have A, B, C, they are all positive integer, and we have GCD of AB equals to 1, and A divides B times C, then this will tell us with these two conditions, we can conclude that A divides C. Now the GCD of AB equals to 1, but we mentioned that this means they are relatively prime. And also this means A and B don't share a common factor. Another word, A will not divide B. And not only that, since their GCD is 1, none of the factor of A divides B. Right, since they don't share any common factor. Now with that, right, you know A does not divide B, and if you know A divides BC, and since A and B don't share a common factor, then A must go into C in order for A divides BC. So when you have A divides BC, but A have a GCD of 1 with B, then A divides C. However, it's not enough to just say if A does not divide B, A divides BC, then A divides C. We can just replace the GCD equals to 1 with A does not divide B. Can anyone give me a counter example? Give me an example of A, B, C, where A does not divide B, A divides BC, but A does not divide C. Anyone give me a counter example of this case? Can you give me an example of ABC where it will satisfy the condition here, but it will fail with the conclusion here? Okay, let's see. Do we agree that 4 does not divide 6? So I let A here to be 4, B here to be 6. But do we agree 4 divides 6 times 10? So here is your B and C. Your C is 10. Do we agree 4 divides 6 times 10? 6 times 10 give you 60. 4 go into 60. Do we see that? Now, does this implies 4 divides 10? It's 4 divides 10. Does 4 go into 10 evenly? Okay, I see people say yes. Is 10 a multiple of 4? In other words, if 4 go into 10, that means 10 is multiple of 4. So it's not true. So we found a counterexample. Now, do we see why is this false? right? Even though 4 does not go into 6, but the GCD of 4 and 6 is 2. So even though 4 does not divide 6, but factor of A divides B. So you can have factor of A take care part of the B. And then let C take care rest of the factor of A. So that's why you need to have GCD of AB equals to 1 and A divides BC to conclude that A divides C. If you just have A does not divide B and A divides BC, then A divides C, this is not enough. Right? Only when none of the factor of A divides B, then A will divide C. Any questions here? Okay, so if you look at the next lemma, it's kind of generated from the first one. Now, if you have a prime, then if this prime divides some factor, if this prime divides some prime factor, or just product of some number, then you know P, this prime, will divide one of the factor. Now the reason is if you just apply the rule from the first lemma, you will just check, does P divides A1? Does P divides A2? You just check each one. You will check what's the GCD of P and AI. Now, since P is a prime and AI is an integer, prime means the only factor is 1A itself. The only positive factor is 1A itself. So that means when you look for the GCD, GCD is the greatest common divisor. Now the only possible divisor or positive divisor for P is 1 or P. So that means when you look for the greatest common divisor, your answer will either be 1 or P. Now if your answer is P, well, that means P divides P, P also divides A, then you know P divides AI. Now if the GCD is not P, then your GCD must be 1. 1 means none of the factor of P go into AI. So if you check for each one, if the GCD of P and A1 is P, then you find it. Then you find P going to A1. If the GCD is 1, then you know P does not go into it. Then P will go into the rest of the product. Then we'll just keep going, and eventually P need to divide into one of the factor. Any questions here? Okay, next. Okay, earlier when we talk about modulus operation, where we learn about addition, multiplication, I ask you to do subtraction. Now we never really did division, right? And then the reason we have for that is when we divide, we don't always get integer. But with the modular, we can technically divide if your modulus satisfies certain condition. So if you have AC congruent to BC modulo M, and normally you want to, but you see C go into left-hand side and right-hand side. Like after you divide the C, you still get the integer. You will still get integer A and integer B. So you want to divide C. So if you see a number go into both left-hand side and right-hand side, you can divide them. Now, the only thing you need to be aware is the number you divide must have the GCD of 1 modulo M. So you must have so the GCD of the number you divide, the C, with the modulus, it need to be relatively prime. So I can give you an example. Do we agree 6 is congruent to 16 mod 5? Yes, okay. Now, what number that will go into both 6 and 16? Well, R is not, so if you say 1, we don't want to divide it by 1. If you divide it by 1, nothing happened here. What number can we divide between 6 and 16? What's their common factor? What's their uncommon divisor that we can divide? Okay, 2. Now the GCD of 2 and 5 is 1. So we are good to go. We can divide them. Now if you divide them, 6 over 2 will give you 3. And 16 over 2 will give you 8. Then we have 3 is congruent to 8 mod 5. Is this true after we divide? Is 3 congruent to 8 mod 5? Yes. So we know this is true. Now, if you look at another example, we still have 6 congruent to 16. Now, instead of mod 5, let's do mod 10. Now, between 6 and 16, we can still divide it by 2. And if you look at the GCD of 2 and 10, what's the GCD of 2 and 10? It will be 2. So if you just simply divide the 2 from 6 and 16, you'll get 3 congruent to 8 mod 10. Is that true? Is 3 congruent to 8 mod 10? No. Right, so to fix it, we will divide the modulus by the GCD of the number we divide and then the modulus. Which means we will also divide the modulo by 2. So we have 3 congruent to 8 mod 5. Now the reason we didn't divide earlier, because the GCD is equal to 1, right? With the question, the GCD is 1. So the number you divide and the modulus are relatively prime. So even if you divide the GCD, it will not change your modulus. So to generate this theorem, we know you can always divide a number as long as you also divide the GCD of C and N. So that will leave you A is congruent to B mod M over GCD of C and N. Okay, so the first thing you need to check if you want to divide is the number you divide to the left-hand side and right-hand side produced integer. But you need to make sure after you divide, your number still remain integer. And the number you divide, it's relatively prime with the modulus. If not, you need to reduce your modulus as well. Any questions here? Okay, if not, we will move on. Okay, so we will back to the congruences. So now we have linear congruences. Okay, and then you see a variable x. So just like the linear equation, now you want to solve for the x. So if you look at the first question is asking you, what value of x, well, we multiply 3, that will give you 2 mod 5. Now, when we look at modulo 5, how many different possible solutions are there when we are in the environment of modulo 5? There will be 5, right? Because mod 5 break all the integer into 5 categories, right? From 0 mod 5 to 4 mod 5. So instead of checking every single integer, you just need to choose one from each category. So you can just check x for the range 0 through 4. Does 0 work for x? Does 3 times 0 give you 2 mod 5? No. So if you keep going, does 1 work? Does 3 times 1 give you 2 mod 5? No, right? 3 times 1 give you 3. 3 is not congruent to 2 mod 5. Now, if you keep going, if you check 2, is 3 times 2 give you 2 mod 5? 3 times 2 give you 6. 6 mod 5 will reduce to 1. So 2 does not work. Now again, you check the 3. You have 3 times 3. That will be 9. 9 mod 5, that will reduce to 4. It does not work. So you keep going. Now finally you check the 4. Now if you do 3 times 4, that will give you 12. What's 12 mod 5? Mod 5 will give you 2. Or you can subtract 10 from that. 10 is multiple of 5. So since 3 times 4 give you 2 mod 5, then you know your x will congruent to 4 mod 5. So not only 4 work, any x that congruent to 4 mod 5 will be a solution. So 9 will also work. 9 will also work for the x. 14 will also work for x. If you want smaller number, -1 also work for it. But all the solution will belong to 4 mod 5. It will belong to these congruent classes. So no matter which value you find, eventually you want to put it into the least non-negative residue form of the congruent classes. So you will always put your answer in the LNR form. You will reduce it. Now let's look at the next number. Right, so next number we have 3x congruent to 2. Instead of mod 5, we have mod 6. So for mod 6, we know there are 6 possible solutions, right? From 0 mod 6 to 5 mod 6. Now, can you find the solution? There are only 6 there to check. And you can eliminate the 0 almost immediately. 3 times 0 give you 0. It does not give you 2 mod 6. They just keep going. Can you find a solution? Anyone? Did anyone find a solution? Can we just check 0? 0 does not work. So let's check for 1. 3 times 1 give you 3. It does not congruent to 2 mod 6. Now if you check 2, 3 times 2 give you 6. 6 congruent to 0 mod 6, so it does not work. When you check 3, 3 times 3 give you 9. 9 mod 6 give you 3, so it does not work. When you check for 4, 3 times 4 give you 12. 12 mod 6 give you 0. So it does not work. And then when you check for 5, 3 times 5 give you 15. 15 mod 6 give you 3. So you just check all the number from 0 to 5. None of them work. Now if you keep going, 6 is the same as checking the 0. So we try all possible solutions. None of them work. So it seems that we have no solution here. Okay, let's look at the next one. 4x congruent to 2 mod 6. And again, since we are looking at mod 6, the possible solutions are from 0 to 5. So can you give me an x that when you multiply 4, that will give you 2 mod 6? Anyone? If people say 2, let's check. 4 times 2 give you 8. 8 mod 6 give you 2. So 2 works. Anything else? Did we try all the number between 0 and 5 yet? So we know 2 work. Is there any other number work? Okay, 5. So let's check 5. 4 times 5 will give you 20. 20 mod 6 will also give you 2, right? You can subtract 18 from it. 18 is multiple 6. So 2 and 5, both 2 and 5 modulo 6 work for x. So we just find this linear congruences with multiple solution in modulus. Okay, let's keep going. Now let's say we want to find x for 56 times x congruent to 2 mod 79. How do we check that? For modulo 79, how many possible solutions are there? How many possible solutions for modulo 79? Okay, some people say 78, right? There are 79 categories, but normally we eliminate the 0, right? Because you know 0 doesn't work, right? So if you knock down the 0, you still have 78 to go. You have 78 to check. So do we want to check them one by one? No, right? So it will be too much to check. So it will not be like an ideal way to solve linear congruences, right? So we can check all the solution in the previous examples because the modulus is small enough. But you can imagine when your modulus is like 79, it's like 3-digit number, 4-digit number, it's like much larger number. You don't want to check all possible solutions. So we need to find other way to do it. Now this is a linear congruences. Now imagine you have a linear equation. If you have 56x equals to 2, or you have a linear equation here, how do you solve for x normally when you have a linear equation? Okay, I see people say isolate the x. How do we isolate the x? Okay, I see people say divide both sides by 56. Right, so if we divide both sides by 56, it will get rid of the 56, and then we'll have x equals to 2 over 56. Now this method works in the linear equation. But when we have linear congruence, when we are dealing with congruence, we know we can always divide. In fact, if you look at the example here, when you divide 56 on both sides, the left-hand side is probably still an integer, but the right-hand side have 2 over 56. It's no longer an integer. So you can divide 56 directly. So if I tell you you can divide, you can use anything else except the operation divide in this linear equation. How can you isolate the x? How can you solve for x without using divide? You just can't mention divide. How can you do it? Can we get away with divide and still isolate the x? Anyone? I see people say subtract 55x. If you subtract 55x, then you move the x to the other side. Then you both left hand and right hand side have x. You don't want to do that. Okay. The only thing you are not allowed to do is division, right? Since we are dealing with equation, you could have fraction. but you could have number that's not integer. Right, just we don't want to use division because division don't always work in the linear congruences. So besides division, is there anything you can do? Is there something that's similar to divide 56? But you just don't mention the word divide. Like, can you multiply instead? Okay, I see people say multiply the inverse. So what's the inverse here? You want to find inverse of what? $56. So what's inverse of 56? One over 56. So if you multiply 56 multiplicative inverse, okay, I see people say 1 over 56 is not integer. We are allowed to have fraction in the linear equation. It just, we are not allowed to have fraction in the congruences. But here we still have a linear equation. We just don't want to do divide because division will cause problem in congruences. So we want to avoid that. But we can multiply the inverse. Okay, so 1 over 56, it will be a multiplicative inverse for 56. But it will not, it will obviously not be the inverse for the multiplicative inverse of 56 mod 79. So we will multiply 1 over 56 to the congruences. But that works in this equation. Right, then you have x, right? You have 1x equals to 2 over 56. Now 1x is the same as x. So you solved for this equation. Now if we come back to the congruences, what does inverse do? Inverse is not always the reciprocal. Right, it's a reciprocal in the real number when we do operation, because whenever you have a non-zero integer, we multiply the reciprocal, it will give you 1. So what inverse does for the multiplicative inverse is when you multiply the number with its inverse, you want to get the multiplicative identity, which is 1. So with the linear congruences, we want to find inverse of 56. Then when you multiply inverse of 56 on both sides, now 56 times 56 inverse, that will give you 1x. Then you will solve 1x equals to 2 times 56 inverse mod 79. Now, of course, the inverse here, 56 inverse mod 79 here will not be a fraction. It will be an integer. So you can do that. But how can we find inverse? Okay, again, inverse, I'm using the little -1 here to represent the inverse. So a number multiplied by its inverse, it will return to you the multiplicative identity. Identity means when you multiply or apply the operation to the identity, it will give you Excel back. Now for multiplication, everything times 1, it does not change the number. So 1 is the multiplicative identity. So for the inverse, if you find the inverse for a number, that means when you multiply the inverse with your number, you will get 1 modulo m. So if you look at here, let's look at 2 mod 5. Can you find a multiplicative inverse of 2 mod 5? In other words, what number do you multiply by 2 that will give you 1 mod 5? Can you find a number that when you multiply by 2, that will give you 1 mod 5? So as if you say 3, so if you check 2 times 3, give you 6, 6 is congruent to 1 mod 5. So 2's inverse, it will be 3 mod 5. Okay, now if you look at 3 mod 6, does 3 mod 6 have inverse? What's the inverse of 3 mod 6? So what number do you multiply by 3 that will give you 1 mod 6? Okay, I see people say you can't find any of them. It does not exist. Now what about 4 mod 6? Can you find anything that multiply by 4 that will give you 1 mod 6? Okay, does not exist either. Now what about 5 mod 6? Anything that multiply by 5 give you 1 mod 6? Okay, CPO say 5. So if you check 5 times 5, that will give you 25. 25, you can subtract 24. That's multiple of 6. So that will give you 1 mod 6. So inverse of 5 is just itself. So we see sometimes the inverse does not exist. Right, so for 3 mod 6 and 4 mod 6, the inverse does not exist. Now, do we see why? If the inverse exists, that means we want to find 3 times a number. Right, let me use x. We want to find 3 times the number x that will congruent to 1 mod 6. Now this means 3x and 1, since they are congruent, they belong to the same congruent classes. And if they belong to the same congruent classes, then you know the difference between 3x and 1 is multiple of 6. Then you know 3x plus some multiple of 6 will equal to 1. Right now, this k could be negative, right, to bring the number down, or the x could be negative. So this means 3x plus 6k need to equal to 1. Now, if you look at 3x plus 6, what kind of number is 3x plus 6? And again, x and k are just some integer. So if you have 3x, 3 times the integer plus 6 times the integer, what do you know about this number? It's multiple of 3. Now, if you look at the right-hand side, if you look at the 1, what do you know about 1? Okay, I see people say it's a residue. It's 1 a multiple of 3. No, not multiple of 3. Now, can you have an equation where one side is multiple of 3 equals to a number that's not multiple of 3? Can you have a multiple of 3 equals to a number that's not multiple of 3? So the answer will be no, right? It's impossible. Now again, let's check 4 mod 6. Now in order for 4 mod 6 to have an inverse, that means 4x will congruent to 1 mod 6. Now again, if 4x congruent to 1 mod 6, that means 4x, if you add some multiple of 6, it will equal to 1, since 4x and 1 are congruent to each other. Now what's the problem here? What can we tell about 4x plus 6k? Okay, it's even. What about 1? One is not even, 1 is odd. So we cannot have an even number equals to an odd number. So the inverse does not exist. So a quick way to find the inverse, or to determine whether, I should say a quick way to determine whether a modulus have inverse, you just need to check the GCD. Right, if you look at here, the GCD of 2 and 5, it's 1. They don't share a common factor. The GCD between 3 and 6 is 3. They share a common factor of 3. So you know the left-hand side will be multiple of 3, but right-hand side you want it to be 1. And then here you have 4 mod 6, right? Then you're left, and then GCD of 4 and 6 is 2. You see left-hand side is an even number, right-hand side is not. Right, so the only thing go into the right-hand side is 1. So you need to have the GCD equals to 1 in order to have an inverse. Now, if you look at 5 mod 6, GCD of 5 and 6 is 1. So that's why inverse exists. Okay. Now for inverse, if you have A and M are relatively prime means GCD of A and M is equal to 1, then the inverse of A modulo M exists. So you need to have GCD equals to 1 in order for the inverse to exist. Any questions here? Now, if we look at those following modulus, can you tell which of the following modulus have inverse? Does 3 mod 12 have inverse? Okay, the answer is no. Right, if you check the GCD of 3 and 12, it's equals to 3. Now, what about 4 mod 12? The answer will be no. Right, again, the GCD of 4 and 12 is 4. Now, what about 5 mod 12? So it will be yes, If you check the GCD of 5 and 12, it's 1. So we know inverse exists. Now what about 6 mod 12? The answer will be no. Right, again, if you check the GCD of 6 and 12, is equal to 6. Now what about 7? 7 mod 12. The answer will be yes. GCD of 7 and 12 is 1. Now, since we know 5 and 7 have inverse modulo 12, what's the inverse of 5 mod 12? What number do you multiply by 5 that will give you 1 mod 12? Let's if you say 5. So if you check 5 times 5 give you 25. And 25 you can subtract 24, right? Multiple of 12, and that will give you 1 mod 12. So you have 5 times 5 congruent to 1 mod 12. That's true. So inverse of 5 is just 5 itself. Now what about 7? What's the inverse of 7? Since we know inverse of 7 mod 12 exists. Okay, will be 7. 7 times 7 give you 49. Now 49, you can subtract 48. 48 is multiple of 12. So 49 minus 48 give you 1. So 7 times 7 is congruent to 1 mod 12. So inverse of 7 is 7. Now let's move on. Before So before we get into this, let's see. Let's look at this one. Let's find inverse of 13 mod 27. First of all, does the inverse exist? How do we check that the inverse exists? Right, so the first thing we should do to look for the inverse is to check does the inverse exist by GCD. Right, so we want to find GCD of 13 and 27. Now, whenever we look for the GCD, right, in here we know it's 1. But for the more large number, but when you have more complicated number or more complicated GCD, you should always use the Euclidean algorithm. So you should use Euclidean algorithm to solve GCD. Now, even you know the GCD is equal to 1, I will still recommend you to do a Euclidean algorithm since we need it later. So let's do the Euclidean algorithm. For the Euclidean algorithm, we will take the larger number and we see how many times the smaller number divides to it. So we have 13 times 2 plus 1. Now, once you have remainder equals to 1, you can technically stop there, right? In all the previous example, when we look for the modulus, we stop when we hit 0. But besides 0, we can also end at 1 because we know the smallest divisor is 1. You cannot have any divisor smaller than 1. So once you hit 1, you know the next line you will hit 0. So if you hit 1, you can just stop there and then say the GCD is equal to 1. Right? Because if you just do a shift and then check it one more time, right? Since you have one of the factor now it's 1, you have 13, and you see how many times that's 1 going to 13. Well, 1 will always go into an integer. And then you will hit 0. So that's why when you see 0 as a remainder, you can always stop there and then say 1 is the GCD. Right. So once we find the GCD, we know if the GCD equals to 1, then the inverse exists. If the GCD does not equal to 1, then inverse does not exist. Okay, so that's the first thing you check. Now the second thing is you want to put it into linear congruences and linear combination form. So you want to find so since we know inverse exists, we want to find 13x. Okay, so the second thing we want to solve for x, which we use x as the inverse. We want to solve for x of 13x congruent to 1 modulo 27. Right, so the x here is the inverse. Now to do that, the first thing you do is put it into linear combination form. Well, we know if 13x congruent to 1 mod 27, then you know 13x and 1 are belong to the same congruent classes. Then 13x, you will be able to find 13x plus 27k equals to 1. Now, if you look at it, what does this remind you? When do you see 15x plus 27k equals to 1? But we have a linear combination here. When do we see linear combination? In the Bundruth theorem. So by the Bundruth theorem, we know this is true, where we are able to find x and k to make this linear combination true, since the GCD of 13 and 27 is equal to 1. So we know it exists. So we can just solve for the linear combination. Now I see people say x equals to -2 and k equals to 1. So to solve for the linear combination, you will do the Euclidean algorithm backward. So you will rewrite the 1. So you will have, so from here, you will have 1 equals to, now you put it into linear combination. So you have 27 times 1 plus 13 times -2. Now, if you want to put it into that form, then you have 13 times -2 plus 27 times 1 equals to 1. So what's your x? So your x now is -2, and then your k is equal to 1. Then what does your x equal to? Your x will congruent to -2 modulo 27. And -2 is congruent to 25. So you know the answer will be 25 mod 27. So once you solve for the x, if the question just asks you for the inverse, then you should reduce to the O and R form. Any questions here? So this is how we will find the inverse. Right? So we will use the Euclidean algorithm and then doing it backward. And once we find the inverse, if we want to solve, right? So here we just find the 13 inverse is congruent to 25 modulo 27. Now, if you want, you can also use -2, which is also congruent to -2. Now here, right, to solve for 13x congruent to 11 mod 27, we can multiply inverse of 13 on both sides. And we know inverse of 13 is equal to 25. So you can multiply 25 on both sides. And that's also congruent to -2. So to make it easier, you can just, well, it's, so we know one x will congruent to 11 times 13 inverse. Now 13 inverse is congruent to 25. Now 11 times 25, you can compute it. Or instead of multiplying 25, we know 25 is congruent to -2 mod 27. So we can just multiply by 24. That will give you -22. Now -22 is not in the reduced form. So we should always find the final result in the reduced form. Then we have x congruent to -22 is too small. You add 27 to it. Then you have x congruent to 5 mod 27. Any questions here? So with this example here, you should be able to solve the question we had earlier. Right, so this is a question we have earlier. If we want to find 56x congruent to 2 mod 79, right, again, you will find the inverse of 56 mod 79, and then multiply it to both sides. So try to do this one on your own. Okay, so we will end it here, and then we will pick up from here next class. Okay, have a nice weekend.